Example 13 says, on the same diagram, sketch the graphs of y equals 5 sine of x and y equals 5 sine of 2x from 0 to 2 pi. So what I'm going to do is make my axes. So instead of using degrees like we have been, we are just now going to use radians. So 2 pi is now like 360 degrees, 0 goes back. We can cut them into chunks, right? We can cut them into halves. It makes it very nice. So we are looking at y equals 5 sine of x. The amplitude in this case is 5. So we know that we're going to be talking about values that could be going up to 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So this is like -5, and this is 5. So we want to graph y equals, let me use blue, y equals 5 sine of x. Okay, so we need to think about what our values are. So the sine of 0 is 0. At 90 degrees, or pi over 2, sine is as a max, so it's a value of 1. So 5 times 1 makes 5. Sine of pi is 0, and the sine of 3 pi over 2 is -1, so -1 times 5 makes -5. And here we go. So this is our sine function. Thus, y equals 5 sine of x. Now, what is happening when we get 5 sine of 2x? Now, what the 2x does is it is doubling our angle as we move along. So what's fundamentally happening is that it is accomplishing the same thing twice as fast. It is doing 2 of these rotations in the same time that the original function takes to do 1. So if you want to think about it this way, so like for 5 sine of x to be a value of 1, we know that, or excuse me, that if the sine of x is 1, we know that that happens at 90 degrees, or at pi over 2. So it's the same idea if we do the sine of 2x, but in this case we would have that double some angle would be at pi over 2, right? And so that would mean that x, the angle that we're looking at, would actually be half of that angle. So how you can think of this is in a couple of ways. You can kind of divide up the maxes and the mins by 2, by a factor of 2, because it's going to move that far. So each 0, divide that by 2 and place it in a new spot. So we have 0 here. So 0 divided by 0, or 0 divided by 2 is there. It's at 0. Now the next 0 is at pi. Well, that means that it'll become at pi over 2, because we would divide that by 2. The next 0 occurs at 2 pi. Okay? So that would occur at pi. Okay? 2 pi over 2, right? We divide it by 2, does that. Now, what you can see is actually this would repeat itself again. So we're going to have another 0 there and another 0 there. So periodic, or these functions are periodic. They work this way. So we can kind of safely assume that that's what's going to happen. Now, what about maximums and minimums? So we want to do the same thing, right? So we want to move them and divide them by 2 so that we can figure out what the new one's going to be. So if this first maximum occurs at pi over 2, so that it's going to occur twice as quickly now. Same thing for this one. 3 pi over 2 goes to 3 pi over 4, right? 3 pi over 2 over 2 goes to 3 pi over 4. Now check this out. It did the same thing that y equals the 5 sine of x did, but it did it in pi instead of in 2 pi. And now guess what? It's going to do the same thing again. it goes through 2 of its entire cycles in the time that it takes the other function to do 1. That's what that 2x does, is it halves the period, or it doubles the number of iterations that sine will go through in that time. So we can see what's happening during that span. So the second part of the question says, sketch the graph of y equals 5 sine of 2x minus 2 by adding a suitable straight line. State the number of solutions of the equation 1/2 times 5 sine of 2x minus 2 equals -3/2. So interesting. All right, so we are going to go to the next page and we are going to graph this. So it said y equals 5 sine of 2x minus 2. So if we think about this graph, it's going to be the same as the green graph, but we're going to be dropping everything by 2 because that minus 2 is on the outside. So we're going to need more negative numbers now than we had before. So I'm going to have this line. We had -5, so now what I'm going to have is 1, 2, 3, 4, 5, 6, 7 should. And you can see -1, -2, -3, -4, -5, -6, and -7. So this could be this could be complicated if we don't think about it in the appropriate way. Now, what I suggest doing for a problem like this, in order to kind of get an understanding of how you can make this easy on yourself, is think about the graph at the top. So it's centered at 0. Now, this graph is being dropped by 2, so we're going to center at -2. And we're going to make everything based off of that. Okay, so imagine we're going to be basing everything off of that. So the green graph that we had before was a 0 here. We had a maximum in the middle. We go back to this point. We go to a minimum, which, again, it was going to be -5. We take 2 away. We get to -7. We go back up to this line is at 2. Go back, or -2. We go up and down and up and down. And so we end up with, oops. Right, so something roughly looking like that. Now we don't need our white line anymore. So this kind of gives us some ideas as to what we might possibly be looking at. But it follows the same rules. We just shift it down too. Now the second part asked us, by adding a suitable straight line, state the number of solutions of the equation 1/2. So let me write this. 1/2 of 5 sine of 2x minus 2 equals -3/2. So how could I guess as the number of solutions that this would have? So on this interval, 0 to 2 pi. So this graph here, so what we need to figure out is how are we going to alter this thing? How do we alter this, or is it -3/4 or -3/2? Sorry, -3/2. So how are we going to alter? How is this altering it? We know this graph. That's the green graph right here. So if we have a half of that, what's going to happen is it would actually squish the graph. But we don't actually need to think of it in those terms. What we could do is we could multiply both sides by 2. And that would return us to our green graph. Well, if we multiply both sides by 2, this would become 5 sine of 2x minus 2. And this would become -3. So how many times does this graph equal -3? So let's go and think, okay, so we got -3 here. We're going to draw a straight line across. So how many solutions does this have? 1, 2, 3, and 4. 4 solutions. That's what they want us to do. So you can use this type of thinking to help figure out how many potential answers you may have. Now, the number of solutions will vary depending on what kind of solution they're asking about, where your graph is centered, what the period of your function is. But you'll see a pattern develop over time that will make things a little bit easier for yourself.